to speak. Okay. Yeah, first time to speak in India, at least virtually. So today I'm going to talk about Kakeya or Nikodym sets associated with spheres. So let me first review the usual Kakeya or Nikodym set associated with line segments. So Kakeya set is a set of Euclidean space containing a unit line segment in any direction, in every direction. Okay. And Nikodym set is a cousin of a Kakeya set. So this is a set in Rn. There are some other versions of definition, but let me use this definition. Set in Rn containing for each point x a line Lx, let's say a unit line segment so it's supposed to contain unit line segment containing x, okay, except possibly for the point x. Okay, so let me modify this a little bit. For each x in B1/2, so this is the set of all points in the ball of radius 1/2, so that the diameter is 1/2. So here's an example. So B1/2, where the ball of radius 1/2 is an example of Kakeya set. So this is because for any direction, okay, this set contains a unit line segment. This is also a Nikodym set because for any point in this set, any point x, we can find this line. Okay, this is a unit line segment passing through the point x. Okay, so if this is x, I can find this unit line segment. So this set is an example of Kakeya set and a Nikodym set. So main question is, how small can those sets be? And some surprising result due to Besicovich and Nikodym is that there are Kakeya sets or Nikodym sets of zero Lebesgue measure. Okay, so it means that Kakeya set and Nikodym sets can be very small. And on the other hand, because it contains a lot of line segment, it shouldn't be too small. And this is the Kakeya conjecture regarding the Hausdorff dimension of those sets. So any Kakeya or Nikodym set in Rn must have the largest possible Hausdorff dimension. And okay, saying that Kakeya set or Nikodym set cannot be too small. This is a theorem in dimension 2 on the plane, but this is an open problem in higher dimensions. And this is quite an active area of research and bringing many new tools into play. Are there any questions or comments so far? Okay, so feel free to interrupt me if you have any questions, or you can maybe write your question in the chatting if you have. Right, now I'm going to now look at a couple of examples in the when we replace the line segment by spheres. Okay, one example is given by this set, this kind of set B. So this is a set containing a sphere centered at every point. In Rn. Okay, so if I fix a point X here, then there is a corresponding circle or corresponding sphere. And for other point, I have another sphere centered at that point. Okay. So one can ask whether there is a set, such a set with Lebesgue measure equals to 0. But this question was answered in the negative, that any such set E must have positive Lebesgue measure. Okay, this is a result due to Stein and Lebesgue and Malmström. And this statement follows from the LP boundedness of the spherical maximal function. Now here is now another example, so-called BRK sets. So now we consider sphere where sets containing a sphere of every radius. So this is a set containing sphere of radius 1 and radius 2 and radius 1/2 and so on. So those sets are called BRK sets. And one can also ask whether there are BRK sets of zero Lebesgue measure. And this time, the answer is yes. So there is a BRK set of zero Lebesgue measure. So this is due to Lebesgue and Rado and Kinney, and in high on the plane, and in higher dimension this was obtained by Kakeya and Wolf. The natural question is whether such a set cannot be too small in the sense of Hausdorff dimension. And this was answered by Kakeya and Wolf, and also Wolf. Namely, any BRK set in Rn must have Hausdorff dimension n, okay, the largest possible dimension. So let me just comment on this result. So in the case of Kakeya problem and Nikodym problem for the line segment, the problem is more difficult in the case of higher dimension. But for the case of BRK set, the problem is actually easier in higher dimension, and it's harder in the dimension 2. Okay. And that's because the corresponding or the main estimate that is required in higher dimension turns out to be L2 estimate, while in the 2-dimensional case, the required estimate is L3 estimate, which is more difficult. So that was the work of Kolasa and Wolf, and also by Wolf.
Is there a full form of BRK sets? Lebesgue, I see.
Can you say that again?
Yeah, I think I got my answer. So BRK stands for Lebesgue, Rada, Kinney, right?
Yeah, I think so. Yes.
Okay.
And also, is there any connection between the this BRK set and the first one, Lebesgue or Kakeya set?
Yeah, I think there are connection, and it seems that their discovery of BRK set uses somehow similar approach for the discovery of Kakeya set of zero Lebesgue measure. So yeah, there should be some. Yeah.
Thank you.
Okay. Great. So now let me talk about another class of sets containing a family of spheres. Which is the main topic for this talk, which is Nikodym set for circles. So this is a set of R2 containing for any point on the plane a circle through the point, except possibly for the point X. Okay, so here, if we are given a point X, there is some circle. So the set is, set contains a circle passing through the point X, except possibly at the point here, X. So X can be here. Can I find another circle like this? And in a relatively recent work, it has shown that there is Nikodym set for circles of zero Lebesgue measure. And this is also obtained by Ellen Zhang and Sony. Okay, so then this opens up many new questions to explore. For example, what can you say about the Hausdorff dimension of Nikodym set for circles?
The circles can be of any radius.
Can you say that again?
The circles can be of any radius or unit radius.
I mean the centers of the
A
circle.
circle passing through the point X of radius 1 radii or
Yeah,
any radius.
any radii.
Okay, thank you.
But actually, their result also states that there is a Nikodym set for unicircles. Namely, for every x, there is a unicircle through x, except for the point x. Oh, sorry, here I should maybe modify this a little bit. So except possibly for one point on the circle, for one point on the circle. Okay, so giving a bit more flexibility.
And the restriction on x is any x in R2.
Yes, any x in R2, it contains a circle except for one point on the circle through x. Okay. So one question is about their Hausdorff dimension, and another question is about the version in possible analogues in higher dimension. And this is the main topic of study in a joint work, which is an ongoing joint work with Ellen Chang and George Dosidis. So let me first define what we mean by Nikodym set for spheres. Okay. So we can say that a Nikodym set for a sphere is a set containing for any x in Rn, a sphere let me denote the sphere by Sx, sphere through the point X, except possibly for perhaps one point on the sphere. But we actually do not have such a result, but instead we consider a class of Nikodym set where it contains a sphere through X, okay, except possibly for X intersected with Vx for some affine plane Vx. So what we require is for given x, we consider a sphere, okay, except possibly for a subsphere or lower dimensional sphere. So this is the picture here. So we call such a set to be Nikodym set for a sphere, and ask for whether there are Nikodym sets for a sphere of zero Lebesgue measure. Okay. And here is our main theorem. So firstly, the existence of
Just one question. So Vx is an affine plane which may not pass through X, or it passes through X. I think there is.
It may not pass through X, but
okay.
It's supposed to pass through the center of. We can choose it so that it passes through the center of the sphere.
Okay. Mm-hmm.
Yeah.
Okay.
And just one more question.
Yeah.
In the case of Kakeya function, Kakeya sets for spheres or circles, the Lebesgue measure is positive. That's what you said in the beginning. If you define the Kakeya set for circle or
Well, not sure what. Okay, I think I haven't really said what should be Kakeya set for circles, but BRK sets somehow can be regarded as Kakeya set for circles, I think, because they have some similar property, namely having, existence of such set with zero Lebesgue measure. So, yeah.
okay. And
Yeah.
here you have taken circles and spheres. Instead of that, if you have polygons, for example, are there those kind of sets also studied that you expect,
Okay, at least I can say that this result is available in a larger generality. I think it should contain some more general class of sets, but yeah, not just for the sphere.
I see. But you expect some curvature or what kind of objects conditions?
I think curvature is not really required here.
I see.
But I could be wrong. Because I have to look into that.
Okay, no,
to answer your question properly. Okay. So yeah, one thing that I can say is that this kind of Nikodym sets for spheres, one can also consider Nikodym sets for rectifiable sets. And there are some analogues for rectifiable sets. Okay. So our main result is that there is a Nikodym set for spheres of zero Lebesgue measure. Okay, and secondly, any must have sphere in Rn. Okay, cannot be too small in the sense of Hausdorff dimension. Okay, so they must have Hausdorff dimension n. Okay. So this can be regarded as an analog of the work of Kolassa and Wolf for the BRK sets. And there is some, and for the statement for the second statement, we consider this maximal function and delta. Here, delta represents some small real number. So this is defined by average. So average over S delta here, S delta means the delta neighborhood of Sn-1, the sphere in n-1 dimensional sphere. So we consider average of F So this is average of F over the sphere X plus T times U plus S delta. Okay, and here there is primum over T from 1 to 2, representing the radius of the sphere. And there's another primum over U. Okay, throughout, okay, which are all the unit element of the unit sphere. So this is okay. So let me explain more about what why we can consider this kind of maximal function. So if when you are given a point X, and let's suppose that U is the unit vector in this direction. Okay, then we can consider a unit sphere passing through the point X, centered at X plus U. So this is the point X plus U. So this sphere is X plus U plus S and -1. Okay. Now we can also consider dilates of this sphere. Okay, so this represents another sphere given by X plus T times U plus S and -1. Okay, so it have radius T, and the center is given by X plus TU. Okay, and this, okay, all of those spheres pass through the point X, okay, which is what we are considering in the case of Nikodym set for spheres. Okay, so in other words, this takes the primum over primum of averages of F over all delta annulus, delta annuli of radius comparable to 1, passing through the point X. Okay, so this is what this maximal function do. Okay, so to prove statement, the second statement, we need to show the following type of estimate. So here, n delta F, the LP norm of n delta F is bounded by C P epsilon times delta 2 minus epsilon times P norm of F for any epsilon. Okay, so this type of estimate for some finite P if we have this estimate, then this implies the second statement in the theorem. Okay, by using some standard argument. Okay, So we prove, so here is a theorem regarding this kind of estimate. So we prove that in the dimension bigger than 3, we show that this estimate, this kind of estimate is valid on L2. So on L2, we have up to some constant, some logarithmic blower in the L2 node. Okay, so this is the case in dimension bigger than 2. And in dimension 2, we prove L3 estimate. Okay, for this maximal function. So yes, so these two estimates imply the second statement regarding the Hausdorff dimension of Nikodym for spheres. So this may be regarded as main estimates. And the proof is okay. And I should mention that the maximal function considered by Kolasa and Wolf for the BRK sets also satisfies similar AP estimates. Okay, in the dimension 2, the maximal function satisfies L3 estimate, and in dimension bigger than 2, they prove L2 estimate. Okay. So now let me give you some examples to get some feeling of this maximal function. So here in dimension 2, let me consider a set E given by a thin rectangle of side length root delta and delta. So it's kind of a net example. And if we consider f given by indicator function of this set, okay, and test this function to the maximal function, what we get is, okay, so this is sphere, okay, a circle of radius, let's say 2, but also same time, the circle of radius 1 also contains this set E. Okay, and for any x on this point, so these two annulus passing through x contains the set E. So for such x, m delta indicator function of E is bigger than or equal to the set E divided by the measure of S delta, which is about root delta. And this is not only true for those x, but in fact, any x in this part. Okay, that's because we can consider annulus of other radius in between 1 and 2. So any x, we can find the annulus passing through this point x, okay, contain this set E. So that's what this maximal function does. So here, from here, we can obtain that the LP norm is bigger than or equal to root delta, because the set of measure of this colored area is about 1. So if we now divide this by the LP norm of this set, we get delta 3/2p. So this is delta 1/2 minus 3/2p. So if we want to prove this kind of estimate, then the sharp exponent should be 3. Okay, so for P less than 3, this type of estimate is impossible. Okay, so this shows optimality of the exponent 3. Okay, so that was the example in R2. In higher dimension, we can also consider net type example like this. But it turns out that net type example are not so efficient, and because in higher dimension, the volume of those root delta cap of the sphere have quite smaller volume compared to other type of example. So another example that I'm going to mention is the following. So here now, let's say we are in dimension bigger than or equal to 3. Then we can consider, we use another paper. So we can consider intersection between, okay, sphere of radius 2 and sphere of radius 1. Okay, then the intersection will be a lower dimensional sphere. So this will be the intersection between these two spheres of different radius. Okay, so this can be maybe set to be half of Sn minus 2. Okay. So we consider the delta neighborhood of this set. Okay. Then if X belongs to the sphere or the larger sphere, this maximal function, okay, applied to the indicator function, is at least the measure of this set over delta, because this annulus contains this set. So this is about delta. So and also any point in between these two sphere. So if X is here, one can consider another sphere with different radius containing the set E. So this is for X, where the measure of this set is about 1. So if we consider the ratio of LP norm, then we get delta over delta square over P. So if we want estimate like delta to minus epsilon, we need to have P bigger than or equal to 2. And this shows the optimality of the exponent 2 in the theorem. Okay. All right. So now let me talk more. Okay, talk another maximal function which is also related. So let's consider a set T in Rn, which is a compact set. And then we consider S sub T of F. So here we consider J2 primum. So we consider a similar maximal function, but without the delta annulus we just take average over a sphere rather than delta annuli. So the supremum is taken over all the radius t, and supremum is taken over translation parameter u contained in the set T. Okay. So when the set T is the set containing the origin, then we see that this is the spherical maximal function. And in this case, we know that this maximal function is bounded on LP if and only if P is bigger than n over n minus 1, which is due to Stein and Bourgain. But then we consider, when you consider T equals to the sphere, n minus 1 sphere, then this maximal function takes averages of the function f over all the spheres through the point x. Okay, so we are considering the sub over averages of f over all spheres through x. Okay, so in this case, here we're considering average like this. And what we can say about this maximal function in this case is that when we consider where for t equals to s n minus 1, the maximal function is not bounded on LP for any finite p. So this maximal function is bounded on L infinity, but it's not bounded on LP for any p less than infinity. And this is a consequence of the existence of Nikodym set for spheres. Now, on the other hand, we can still get some positive results. So to describe this result, we need some definition. So here we consider delta covering number. So this is defined to be the minimal number of delta balls needed to cover the set T. Okay, so for example, n Sm minus 1 delta should be about delta 2 minus n minus 1. Okay, because the dimension is n minus 1. Okay, and our theorem says that if nt delta is less than delta 2 minus s, okay, for any small delta, for some s less than n minus 1. So one can interpret this as, roughly speaking, the set T has dimension less than n minus 1. Okay. So in this case, we can show that the maximal function is bounded on LP for some finite P. For P bigger than 2, in dimension bigger than 2, and for P bigger than 3 on dimension 2. Okay, so we prove some boundedness whenever T have a dimension less than n-1. Any questions so far? Yeah, maybe I will briefly mention how we obtain this this estimate. So for this estimate,
yeah, just one question. So, is
Yes.
there a reason for this jump in the exponent P?
For dimension 2 and 3.
Yes, bigger than or equal to 3, it's like.
Yeah, so here, yeah, for the case, so the estimate is quite similar to this estimate, right? We are considering maybe the limiting case of m delta as delta goes to 0, because we are considering only the sphere, not the delta annulus. And the exponent 2 and 3 is the same here. And the difference is, again, coming from this kind of examples. So the examples are different in, the sharp examples are different in dimension 2 and bigger than, dimension bigger than 2. So there, the dump comes from, I think, this geometric reasons.
Yeah.
And the proof of that last theorem uses this estimate regarding n delta.
Yes, so in n bigger than or equal to 3, so your this kind of NAP example sets are not working, right? You have to consider something else there.
Right. So this kind of lower dimensional sphere, Sn-2, have measure bigger than the set considered in the NAP example. And we want to consider E as large as possible to get the most optimal this lower bound for this maximal function n delta. And these examples also arise in the case of maximal functions for the BRK sets considered by Kolasa and Wolf. And and these examples are actually coming from the paper, also appears on the paper. So we see quite similar phenomenon between these two maximal functions.
Yeah. And so, for example, this Kakeya maximal function that is helpful in proving the Bochner-Ries conjecture, right?
Mm-hmm.
One could. So, is there any such application of these kind of maximal functions where we could prove some results?
Yeah, I'm not aware of any applications to Fourier multipliers.
Okay. Mm-hmm. Okay, fine. Thank you.
Yeah. So yeah, let me just finish maybe last explanation. So for the proof of this theorem, we use the estimate about n delta. In addition, we use the local smoothing estimates for the wave equation to prove this estimate. So combine these two ingredients together, we obtain this theorem. Okay, so although this is nearly sharp when S is very close to n-1, we expect that this exponent should be, this range should be increased for smaller s. So, for example, when the dimension is 0, when the dimension is 0, the estimate is valid for n over n-1. So we expect that for different n, this number should be decreased depending on s. And we're still working on this question. But at this, and there is some, this estimate can be improved for different s, but we don't yet have any optimal estimate except for s near n-1. Okay, so that's all I have to say. Thank you very much for your attention.
So I suppose that in the last theorem, sort of the same techniques work here, whichever you considered for the above n delta, the Nikodym maximal function, or you require,
Yes. So we consider n to be more precise. We study. Okay, we consider. So here, n delta is the case when the set T is Sn-1, but you can also consider n delta sub T, which is delta regularized version of S delta T, ST. So in that case, we replace this set by T, and then we can prove this estimate for T, which have dimension less than or equal to n-1. Okay, so as long as the delta covering number satisfy this estimate, this true estimate continues to hold for any T, for any such T. So we use this estimate and combine it with local smoothing estimates to prove such an estimate. So this kind of idea goes back to the work of Chris Fogg and Andreas Seeger and Mockenhaupt. Their new proof about the Bourgain's circular maximal theorem. So in their paper, they use local smoothing estimate to prove maximal estimate for the spherical maximal function in dimension 2. And and we use similar idea to obtain the last theorem.
so it's like you're looking at the Minkowski dimension here, right? So
Yes.
Okay. Thank you. Thank you for a wonderful talk. And are there any questions? Okay. If not, then let's unmute and thank the speaker again for a really nice talk. So thank you.
Okay, thank you very much.
It was a really good talk. Okay. So I guess we'll also see you during the this harmonic analysis discussion meeting, right? Which is in January. I saw your name.
Yes, I registered. Yes,
Yes, okay.
for the
great.
conference.
So we'll see you in January also then.
Okay. Okay, sounds good.